Okay, let's discuss this question. The graph shows how the velocity of a small car changes with time. So as per the graph, it's a velocity time graph. As per the graph, during the first 5 seconds, there's an acceleration. And then from 5 seconds to 8 seconds, there's a constant velocity of 20 meters per second. And after 8 seconds to 10 seconds, there is a deceleration. Use the graph to estimate the velocity of the car at 3 seconds. So how can we do this? We're supposed to estimate the velocity of the car at 3 seconds, right? So where is 3 seconds? 3 is here. Right. So what is the value? Just an estimation, right? So you will use the graph to estimate this. So you need to identify the midpoint between 2 and 4, where the 3 seconds is, and then take the ruler and over vertical line, right? So you can use set squares also to help you to get a vertical line, proper vertical line. And then from the point, at the point where the graph meets, where the vertical line meets the graph, you need to draw a horizontal line until it reaches the velocity axis, right? And accordingly, roughly you can identify what the value is, right? It's between 10 and 15. So what the value should be? It looks like about 12.5 to me, according to what I have done. So I'll go for 12.5 meters per second. Calculate the acceleration of the car when it is speeding up. How would you calculate the acceleration? Acceleration can be found from the gradient of velocity time graph, right? So you can use the gradient. So acceleration is equal to the gradient. Gradient of the graph during speeding up the acceleration. So what is the height? Height is 20 meters per second. What is the run? It's 5 seconds. So what is our acceleration? 20 divided by 5 is 4 meters per second squared. That is the acceleration. Explain why the units of acceleration are meters per second squared. Right. So whenever we are asked to prove units of a certain quantity, physical quantity, we need to start with a equation related to that particular quantity. Acceleration is a derived quantity. It is derived from the velocity and the time, right? So velocity is also a derived quantity anyway. So acceleration is derived from the derived quantity, which is velocity, and the time, which is a base quantity. So acceleration is equal to change in velocity. Change of velocity over time. So then units of acceleration should be equal to units of velocity, meters per second squared, divided by units of time, divided by time, seconds, sorry. So S goes up, so it becomes s to the power minus 1, and they are being added. So this becomes meters per second squared. So that equals to meters per second squared. Right? So you got to use the equation whenever we are supposed to show the units of a derived quantity. Right. Fourth part, show that the car travels further at constant velocity than it travels when it's slowing down. Okay. So basically we got to compare the displacement of the car during constant velocity and the slowing down. Right. So how do we find the displacement using velocity time graphs? Displacement is equal to area under the graph. Right. So we can find displacement during constant velocity. So displacement during constant velocity is equal to area under the graph of this rectangle. Right. So the height of the rectangle is 20. The width is, you have 8 here and this should be 5. 8 minus 5 is 3. Right. Height is 20. So 20 into 3, that is 60 meters. Right. So there is a 60 meters displacement during the constant velocity. Right. So displacement during deceleration. Right. So during deceleration, we have a triangle. So we got to find the area of the triangle. So the base of the triangle is 10 minus 8 is 2. This is 2. Height is 20 again, right? So it should be half into base, which is 2 into height, 20. So that's 20 meters. Right? So during the constant velocity, uniform velocity, the displacement is 60. During the deceleration, displacement is 20. So there is a higher displacement during the constant velocity. So the statement is correct. Right. It's again a velocity time graph. During the first 5 seconds, there is a positive gradient. So it indicates the acceleration. The car accelerates. So after first 5 seconds until 20th second, the car maintains a uniform velocity of 8 meters per second according to the graph. Calculate the change in velocity of the car during the first 5 seconds. Right. During the first 5 seconds, the velocity changes from 0 the initial velocity is 0, the final velocity is 8 at 5th second, right? So the change of velocity would be 8, but we need to calculate that, remember, right? So when they ask us to calculate it, you can't just state it, so you need to show it. So change in velocity is equal to change in velocity is equal to final velocity minus initial velocity. Minus initial velocity. Final velocity is 8 meters per second at 5th second. Initial velocity is 0 at the beginning. So final answer is 8 meters per second. Calculate the acceleration of the car during first 5 seconds. So you can use the gradient. Acceleration is equal to gradient. Right. So again, highest divided by rise divided by the run. Rise is 8 meters per second. Run is 5 seconds. So 8 meters per second divided by 5 seconds. So I divided by 5, it's 1.6 meters per second square. 1.6 is the answer. Right. So you write the acceleration value on the blank. State the size of the resultant force between 10 and 15. State the size of the resultant force between 10 and 15. Resultant force. How do we find the resultant force now? So to find the resultant force, are we going to use F equals ma? If there is a resultant, if there is an acceleration, yes. But between 10 seconds and 15 seconds, the acceleration is 0 because it's constant velocity, right? Acceleration is 0. If the acceleration is 0, resultant force also should be 0, right? So then what is our answer? Resultant force should be 0, right? State. So since they ask us to state, you don't have to explain or show any calculations or anything, right? So just to state the value, it's 0, right? This table shows data about 2 cars. There are 2 cars. We have a family car and a sports car. The mass of the family car is 1,400 kilograms and the mass of the sports car is 600 kilograms. Sports car is lighter. The time taken to reach 30 meters per second from the rest is 10 seconds for the family car and 5 seconds for the sports car, right? So the initial speed of the cars are 0 from the rest, right? So initial speed U is 0 meters per second and final velocity that they reach is 30 meters per second. Okay. The owner of the family car claims that although the sports car has greater acceleration, it produces a smaller accelerating force than the family divided by the time taken, right? Right. We are going to find the acceleration of the family car. So its final velocity is 30 meters per second. Initial velocity is 0 meters per second. Time taken to reach 30 meters per second is 10 seconds. So it comes to 30 divided by 10, it comes to 3 meters per second squared. That is the acceleration. Right. Now we have the acceleration of the family car. So we can use F equals ma to find the force, accelerating force of the family car, right? So mass of the family car is 1,400 kilograms into its acceleration, 3 meters per second squared. So 1,400 into 3. So it comes to 4,200 newtons. Right. Now we'll move to a sports car, because we need to find the force, accelerating force of the sports car. Right. First, we'll find the acceleration of the sports car. Acceleration is equal to final velocity minus initial velocity divided by time. Final velocity is 30 meters per second. Initial velocity is 0 meters per second. Time taken to accelerate is 5 seconds. So 30 divided by 5 is 6 meters per second squared. Right. Now we have the acceleration of the sports car. So let's use F equals ma to find the accelerating force of the sports car. Right. So the mass of the sports car is 600 kilograms. The acceleration of the sports car is 6 meters per second squared. This is 600. It's going to be 3,600 Newton. Right. So the family car has a higher accelerating force. Now, what is the statement we need to justify here? The owner of the family car claims that although the sports car has a greater acceleration. Yeah. Now we'll compare the acceleration. Acceleration of the sports car is higher. Yes, correct, because it reaches 30 meters per second pretty fast. So its acceleration is higher, and it's double this value. Even though it has a higher acceleration, the great acceleration, it produces a small accelerating force, right? So that's correct. Its accelerating force is correct. It's 3,600 Newton compared to 4,200. So therefore the claim is valid.